Okay, so let's go ahead and get started. As you can see from the agenda, the big topic today is what a MUX is. Okay, and a MUX is going to be part of your next lab design, okay, your lab 3 design, which just like previous weeks on Tuesday, you'll have some information to start the lab, but you won't be able to finish until we talk about other stuff on Thursday. Okay, but before we get going into exactly what a MUX is, there's a couple of definitions here, these 3 words that I just wanted to go over just in a minute or so here at the start. Because, last class we started talking about having inputs and outputs that are more than 1 bit, multiple bits. And, in a diagram, we show when we have a multiple bit input or a multiple bit output with a slash with the number next to it. Well, these definitions have to do with when you have something with multiple bits. In fact, has anyone heard the word byte spelled like a Y before? And knows what it means? What does byte mean in the digital world? Exactly. It's just defined as 8 bits. So, if you have an input or output that's, 8 bits, we'll say that's a byte. Okay. Now, another word that you run across is the word word. And in the digital sense, what word means is the number of bits that is used to represent a piece of data. Also, a word is referred to as how many bits a microprocessor typically can store. In a couple of weeks, we're going to learn about memory and what a register is. And when you take CPE133, which is the follow-on class to this class, you learn that the microprocessor, and I put one of these diagrams on each table. That diagram is the diagram of the microprocessor that you build in CPE133. And what you'll learn in that class is that a microprocessor mainly consists of registers. These devices called registers. And like I said, in a couple of weeks, we're going to talk about what a register is in this class. And, a register is designed to store or hold a certain number of bits. Some microprocessors mainly have registers of 16 bits, some 32 bits, some 64 bits. So depending on the number of bits that a microprocessor typically can store, we say that that microprocessor is that number of bits microprocessor. Like I'm sure you've heard probably, in fact, you might have a computer that's, a 64-bit computer or 128-bit computer. And that's what's meant is that if it's a 64-bit computer with a 64-bit microprocessor, well, most of the registers inside that microprocessor is 64 bits. So if you take a look at this diagram and you look at the various lines that are connecting up these blocks, you'll see the lines with a slash and a number next to it, right? And again, that means, as we talked about last time, the number of bits on that line. So what's the most common number that you see? 32. Right? See this microprocessor in CPE133, it's a 32-bit microprocessor. Okay, and therefore the data, is represented with those 32 bits. So that's what a word is. A word is the number of bits that typically a piece of data has, and it can vary. That microprocessor from CPE133, we have 32-bit words. Your desktop computer might have 64-bit words. Okay, so a word, the number of bits a word has can vary depending on the circuitry, microprocessor, and so on. But in this class, because the follow-on class has 32-bit words, that's what will define our words being 32 bits. All right, well, if a word is 32 bits, Can you guess what a half word is? What is it? Yeah, it's just half the bits of a word. So, you know, if you have a 32-bit word, then your half word is 16. Now, there's also a term that you don't hear quite often as much as you used to, at least back when I was a student. And that's a nibble. Has anyone heard of nibble in the digital sense? Yeah, you don't hear this much anymore because you know, typically you don't have data that's only 4 bits. But that's what a nibble is. A nibble is 4 bits. And back when I was an undergrad, you know, like 8-bit microprocessors were like state of the art. You know, I think when I graduated with my bachelor's, it was right on the cusp of them going from 8-bit processors to 16. This was like early 1980s kind of thing. So back then, you know, sometimes you'd hear the word nibble, but you don't hear that one much anymore. Okay, so anyway, like I said, I just wanted to start this with these several definitions, just because, you know, you'll hear those words, you know, not only in this class, but in your future digital classes. But now let's go over what a MUX is. First of all, MUX is short for multiplexer. So its full name is multiplexer, but we call it a MUX. Oh, before I forget, did everybody get my email? I sent an email over the weekend. I got an email from Mustang News, a student reporter, and she's just interested in talking with students that have tried to get rental computers or rental laptops. So anyway, if you didn't see that email, please take a look at it. And you know, if you're interested in talking with her, she gave her email and I think her text number. Okay, but one thing that we're going to use here shortly when we talk about the MUX is this AND. So remember, we talked about an AND gate, and remember the key feature of an AND gate is that you only get a 1 out when all the inputs are 1. Right? If all the inputs aren't equal to 1, you get it. So we're going to come back to this in a little bit. But first, just some basics on a MUX. So like I said just a moment ago, MUX is short for multiplexer. And this is the symbol, okay, for a MUX. And a MUX always has multiple inputs. So that's why I drew, you know, a couple of lines here, and then I put these dots, because you could have 2 inputs to your MUX, or you could have 4, or you can have 8, or you can have 16. The number of inputs that you have to a MUX is always a power of 2. Okay, so 2, 4, 8, 16, 32, so on. But a MUX always has just 1 output. Okay, so there's multiple inputs, but just 1 output. So, you know, the common size MUXes that we have is, you know, we can have a 2-to-1 MUX. That means 2 inputs, 1 output. 4-to-1, 4 inputs, 1 output. 8-to-1, 8 inputs, 1 output, and so on. Okay, like I said, just keep on going powers of 2. Okay. So you got your inputs, you got your single output. Again, there's always just 1 output to a MUX. And then you have another input that's abbreviated SEL, and SEL stands for select. Okay, and when we discuss how a MUX works coming up, you'll see why that's called select. Okay. All right, so just filling out some of the things here in my little cheat sheet, my little bullet list here. Always 1 output, like we said earlier. And inputs are equal to a power of 2. So again, you know, 2, 4, 8, and so on. Yeah. Oh, question.
Do you include storage like when you raise to the power?
No, when I talk about inputs to the power, I'm talking about these inputs here. Yeah, select's kind of like its own input. So, and you'll see why it's called select even shortly. Okay. Now, each input can either be a single bit or it can be multiple bits. Right? So each input can have, just a single bit or multiple. Sorry. And if I had inputs with multiple bits, well, you would show the slash and how many bits. So, maybe each one of these has 4 bits. They always have an equal number of bits. Like either all these inputs are single bits, or all these inputs are 4 bits, or all these inputs are 8 bits. And also, the output number of bits equals whatever the input number of bits is. So if all these inputs are 4-bit, the output would also be 4 bits. And if all the inputs are a single bit, the output would be a single bit. Okay. All right, now we come to, well, actually, before we talk about the select, one more thing. You see the way a multiplexer works, or the way you can think of how a multiplexer works, it's sort of like an electronic version of a multi-position switch. Okay, so the MUX functions like a multi-position switch. So sort of like a dial. Like a dial might have, 8 things to choose from, right? And with your hand, you twist the dial to what you want to select. Okay. Well, the MUX sort of does that because the select line, okay, the select input is going to determine which output, or excuse me, which input gets connected to the output. Okay. So if we only had 2 inputs, okay, like say we have this MUX. Okay, and I got 2 inputs, my 1 output, and I got my select input. Well, depending on what the value of this select input is, that's going to determine which one of these inputs gets connected to the output. So often you'll see like one of the MUX inputs labeled with a 0 and the other with a 1. So if I put a 0 onto the select line, whatever data is on this 0 input, that's what gets connected to the output. So, like say I had a 0 on this input and I had a 1 on this input. If I put a 0 on the select, this 1 would now be at the output. Right? If I change the select to a 1, well, now this data, this 0 on the 1 input, be connected to the output. So you see, the select, as the name implies, the select is selecting which input gets connected to the output. Okay, does that make sense? Okay, well, let's say I had a MUX that had 4 inputs. Again, always just 1 output to a MUX. All right, well, again, you'll typically see these inputs labeled, 0. Get a new blue here, hold on. So you'll have your inputs labeled with numbers. So, 0, 1, 2, 3. And again, this is the select. So you see here, this is a 4-to-1 MUX. So The select input is choosing which one of these four inputs is going to be connected to this output. So how many bits would this select input have to be in order to choose from four things? It have to be 2 bits, right? That goes back to, I don't know, this is probably what, the 6th time I've written this on the board, that 2 to the number of bits equals the number of values. And remember how we talked about every time you add a bit, you double the number of values that you can represent with those bits. So if you have a 4-to-1 mux, your select input has to be 2 bits, right? Because when these 2 bits are 0, 0, the data on the 0 input is going to be connected to the output. When these select bits are 0, 1, right, a binary 1, well, then the data on the 1 input is going to be connected to the output, and so on. So do you see how this is sort of like an electronic version of a dial, right? Because the select line is sort of like the hand that's going to whatever input we want at our output. Okay. So if I had an 8-to-1 mux, right? If I had 8 inputs, 1 output, how many select bits would I need to choose from 8 inputs? 33 bits. Okay. If you had a 16-to-1 mux, you need 4 select bits. Okay, see how that works? Okay, so does anyone have, so, you know, just to finish this, the select line determines which input gets connected to the output, gets connected to the output. Okay, so any questions up to this point? Everybody got a good understanding what a mux is doing? I mean, you're gonna get a lot of practice with this. Again, this is the basic, but is it making sense? Okay, so now take a look at this diagram, this microprocessor diagram, again from CPE133. Can you tell me how many muxes that microprocessor has? How many? You see 6. Yeah, I think there's 4. At least I count 4. There's one over here. There's one over here by this thing labeled PC. That stands for program counter. Again, you'll learn what the solver is in the CPE133. But yeah, there's one over there. You can see that the one over here by the PC. See how it has a 3-bit select input? But notice it doesn't have 8 inputs, right? It only has 1, 2, 3, 4, 5, 6. That just means that 2 of the inputs aren't being used, or they're not shown. So you don't have to use every input of a device. I mean, sometimes you'll have a device where, you know, you just don't need all inputs. Right, but since we're using more than 4 inputs, we need more than 2 bits, right? Because if we only had 2 bits, we wouldn't be able to select all the inputs there. So yeah, you got a mux here. There's a mux up here by this thing called the rate file. And then there's a couple of muxes over here by ALU. So yeah, there's 4 muxes. The only reason I wanted you to look at that is just so you know that next class you'll be dealing with muxes. So it's not only this class, it's the next class. All right, so yeah, I think the answer to this is 4. Okay, so let's if there's no questions up to this point, let's go ahead and move on. And let's look at the logic circuit that actually makes up a mux. See, this symbol represents a logic circuit like this. In fact, this is a 4-to-1 mux example. Okay. D0, D1, D2, D3, those are my inputs. And again, we just have our 1 output over here. And then S0 and S1, those are our select bits. Again, since it's 4-to-1, since I'm choosing from 4 inputs, I need 2 select bits. Okay. So we're we're gonna come out with what the truth table for this logic circuit looks like. And so you can see in the truth table, I have my select bits. And this is F over here. We're calling the output F. Okay, so I got my select bits over on the input side of the truth table. I got my F output on the right side, like we talked about, right? That's the standard convention. So since I have two bits, two select bits, how many possible combinations do I have? How many? 4, right? 2 to the 2, 4. So 0, 0, 0, 1, 1, 0, 1, 1. So let's first see what the output F is going to be when both select bits are 0. Okay, so this select bit is 0, this select bit. Okay, now before we start, going through that logic diagram, let's back up a minute and go back to an AND gate. Again, we talked about an AND gate. Remember, you only get a 1 out of an AND gate when all inputs are 1. But you see, if we take the AND gate truth table and we split it in half, we can get more insight into how an AND gate actually works. Okay, understand it better. Okay, and what I mean by that, see, if we split up the truth table and then we just look at the top 2 rows, you see what the top 2 rows are telling us? If one input to an AND gate is a 0, does it matter what the other input is? No, why? Because if one input to an AND gate is 0, what's the output going to be? 0. See, that's what the 2 top rows tell us, right? See, one input to an AND gate, if it's a 0, I don't have to know what the other input is. The output's going to be 0 regardless, okay? Okay, now look at the bottom 2 rows of the truth table. Can you see what the bottom 2 rows are telling us? If one of the inputs to an AND gate is a 1, how does the output of the AND gate and the other input relate? Yeah, it's just the output's going to be whatever the other input is, right? So you see, if I have a 1 into an AND gate, the output's going to be whatever the other input is. Okay? So you see, you can learn more about a gate by sometimes splitting the truth table in half and just kind of looking at top and half of the truth table. Okay, and you're going to see how that's going to help us coming up here. All right, but let's come back over to here. And now, I know this diagram's a little busy, if you will. But wherever you see lines crossing, you can see cross there and so on, there's no connection at a cross. Okay, there's no connection. In old diagrams, you don't see this anymore, but in old diagrams, again, back when I was an undergrad, they would do like this. They would show a little hump, so to emphasize there was no connection there, but they don't do that, or I haven't seen it very much anymore. If there was a connection, when lines cross, if they are connected, you'll see a dot like that. Okay. All right, so let's start right here. See, here, this 0 is directly connected to this input of this AND gate. Okay, see that? So it's directly to the input of that AND gate. So since I know this input of this AND gate's a 0, do I have to even think about what the other inputs are? Because if one input to an AND gate is 0, what's the output going to be? Yeah, it's just going to be a 0. See, I don't even have to know what those other 2 inputs are, right? It's going to be 0 regardless. Okay. Also, this 0 from S0, it's connected to this bottom AND gate. So that's going to be a 0. Okay, what else do we have here? All right, now if we look at S1, which is also 0 for this first row, well, this S0 goes to, or S1, which is equal to 0, it goes to this middle input of this AND gate, right? So that's going to make the output of that AND gate of 0. Right, so everybody see how I got 0 for those 3? All right, well, now let's look at this top one. This top one, this input of this top AND gate, it goes to the output of this inverter. We know how inverters work, right? What's the output of that inverter gonna be? It's gonna be a 1 since the 0 is going into it, right? Remember, this is the input side of the inverter, this is the output side. So there's a 1 at the output of that inverter. That's gonna put a 1 at that input of that AND gate, right? So now, now I have to look what the other inputs are, right? Right, because it's not like these cases. Once you have a 0, you don't have to worry about the other inputs. But if you have a 1, now you got to look at the other inputs, right? So look where this middle input of this AND gate goes. It goes to the output of this inverter, right? So it's got a 0 on the input side, so it's also going to have a 1 on the output side. So now that middle input of the AND gate is going to be 1, right? So I got 2 1s. So since these 2 inputs are 1, what is this output going to depend on? It's going to depend on this D0, right? Because since these 2 inputs are 1, if D0 is a 1, I'll get a 1 out. If D0 is a 0, I'll get a 0 out. D0 or is it? It's just a single bit. Yeah, it's just a single bit. So you see, the output of this AND gate is just going to be whatever D0 is. And now these 3 zeros go to the input of this OR gate. And remember how OR gates work? How do OR gates work? What does it take to get a 1 out of an OR gate? Yeah, at least 1 1 at the input, right? So at the input of this OR gate, right? These 3 inputs are 0 because they're coming from the outputs of these AND gates. Well, D0, the output of this AND gate, it's going to determine what the output of that OR gate is, right? Because if D0 is a 0, the output of the OR gate is going to be a 0. If D0 is a 1, the output of the OR gate is going to be a 1. So you see, F is just going to equal D0. So you see, that's how whatever data is on this input, that's how it's getting connected to the output, is by having these AND gates along with these inverters strategically hooked up. So that's the only bit that gets through.
So like a multi-bit input, would you just like hook up a bunch of these?
Yeah, if it's multi-bit, it's the same conceptually, it's just more gates. It's a little bit more complicated to see for the first time. That's why I wouldn't start with it. But yeah, it's the same idea that only one of these inputs is going to be able to navigate through the output. And what you would see, and if you want, we can do another one, but if you understood what we just went through for this top row, the next 3 rows, it's the same idea. It's just that for this row here, 0, 1, it's this AND gate that will allow the data through. All these other AND gates will have outputs of 0. And for this row here, it's this AND gate that will allow the data through, and all the other inputs will have outputs of 0. Right? And if it's this row, it's this AND gate that allows the data through, and these 3 AND gates would have outputs of 0. You have a question?
Put the word connection on. So I can see what the connections are like. You come out a little dot.
Well, what I was saying is, if there was a connection, you'd see a dot. But you see, we don't. Where you see crosses in this diagram, there's no connection. Like there's no connection at this crossing, none here, and so on. If there were, there would be a dot. Yeah, but you see, if there were connections at these intersections, this circuit wouldn't work the way we want it to work. It'd be a different circuit. Yeah, so anyway, if you finish out this truth table, you'd have D1, D2, D3. Okay. All right, so any other questions up to this point? Okay, the next thing we're going to look at is just a timing diagram with the MUX. And the activity for today, that's pretty much the activity is you're given timing diagrams along with the MUX. And usually, if you can understand a timing diagram for a certain device, usually that's a good sign that you understand how the device works. Okay, so in this example, this is the MUX we're gonna use. Okay, so there's 4 inputs, 1 output. So again, this is a 4-to-1 MUX. And I purposely, also notice that each of the inputs is 8 bits. And of course, again, the output is always the same number of bits as what the inputs is. So we have 8 bits here, input and output. Okay, I purposely didn't put the number of bits for the select because I wanted to test you to see if you can tell me. How many bits is that select line gonna be? 3. Yeah, I'm glad I heard both numbers. Because see, this is a common error. Is it 2 or is it 3? It's one of those. How many people say it's 2? How many people say it's 3? How many people don't know? One honest, a couple of honest people. How many people don't like raising their hands? Oh, I didn't catch anybody. Usually somebody will raise their hand. It's like, well, why are you raising your hand? You don't like to raise your hand. Okay, the answer here is 2. Okay, but 3 is a common mistake, and it's an understandable error, but it's still an error. See, what determines the number of bits for the select input is the number of inputs, not the number of bits that each input has. I can understand why someone might say 3 because they see this 8, they think 2 to the 3. But you see, that's not what determines the select bit. The select bits are determined by how many inputs you have. It doesn't matter if these were 32-bit inputs, like on your microprocessor from CPE133, this would still be 2-bit select. Okay, so does everybody see that? Again, I'm glad some people said 3 because, like I said, for a problem like this, that's very common mistake. Okay, so we got our 2 select bits. All right, so now I think this is the first time you've seen this notation. I haven't talked about this 0x, have I? I don't think that we've come across this yet. In timing diagrams, you'll often see 0x. And all that means is that what follows is base 16. Right? So it just means all these values are hexadecimal. Right? And you can kind of see, right? To see where you see CF, 1A, right? Those would only make sense if they were hexadecimal, right? So yeah, that's all the 0x means, is what follows is base 16. Okay. All right, so when you're looking at a timing diagram, and you've seen timing diagrams because you look at those in Vivado, right, to verify that your designs are working. So you know that, t equal to 0 starts on the left side, right? And as time progresses, we just go left to right. Now, where you see like an X, that's when values are changing. So you can see we start out with a select line of 3, right? A hex 3. So what am I going to get at this output F when my select bit is equal to a 3? Right, you're going to get the data AA, right? Because if this is a 3, well, input 3 gets connected to the output F. So we just look at the data. And I'm estimating here. During this time, that's when we're going to have the data AA, which is a 24 hex, right? So this is going to be 0, 24, right, up into this point. Okay, then the select line changes to a 1. So what's going to be at the output now in this select is a 1. Yeah, it's just going to be the data on input CC, right? Because that's the data connected to input 1 of the MUX. So, during this time that the select line is a 1, again, if I'm a little off, forgive me, but during this time, it's going to be this data here. So, it will start off as 22 hex, and then it's going to change to A3 hex, right around here it will change to A3 hex. That's okay, sorry. Okay, and now during this time, the data on input 0, DD. Right, so during this time here, it's going to be the data DD, Right, so it will change the 2A here. And then here it will change the, what is it, FF? Okay, do you want me to keep going or you get the idea? Get the idea? Okay, so again, a MUX is just like an electronic version of a multi-position switch. With the select bits, you're determining which input gets connected to the output, right? You always have one. And MUXes are very common. You'll see they're very useful. Okay, you'll see that in the designs we have coming up this quarter. I think just about all the designs left have MUXes. And then it's very likely in your final project that you'll need a MUX. And as we saw earlier in CPE133, the microprocessor has 4 of them. Okay, and I got to turn the camera so I didn't forget. I'm on a streak, right? This is like the 3rd class I haven't forgot to turn the camera without being told. Let's see. Okay. All right. So like I said, the activity, we'll take a look at the activity coming up, but it's just more practice with timing diagrams and MUXes. Okay, now I kind of want to shift a little bit and go into, well, how you would model or a way to model a MUX in Verilog. Okay, so this has to do with the lab portion of the class. And as an example of how you're going to model the MUX in System Verilog, I have a different device called a comparator. Okay, so you're not using a comparator for lab 3, okay? I'm just using this as an example because this is the class where instead of writing Boolean equations like you have been the previous labs, right? Remember the first lab, right? Your first logic circuit, that was a Boolean expression. And then the locked box, right? You had to do 3 expressions there, right? You did like a reduced SOP, reduced POS, reduced NOR. And then, let's see, the one that was due last night, the ripple carry adder, that consisted of a half adder and full adder. And, you again use Boolean expressions for both those adders, right? Well, the real powerful, thing about System Verilog is, like in other programming languages, you can use if statements. So, we could have you figure out the Boolean expression for this logic circuit and have you write that to model a MUX. But instead, we're going to have you use the power of Verilog. And we're going to have you use an if statement. Okay. So as an example of an if statement in Verilog, I have this comparator. Okay. And a comparator, as the name implies, compares. And it compares 2 inputs. Okay, so a comparator will always have 2 inputs. So here, this comparator has inputs A and B. And then typically a comparator will have 3 outputs: a greater than, a less than, and an equal to. Now, just like in all the other modules that you've designed this quarter, and this is true of any module that you design in System Verilog, you always start out with the module name, and you always start out with declaring your inputs and outputs. Right, so, comparators, the number of bits that the inputs have that are being compared can vary. You can have 2 bits, 4 bits, 5 bits. I mean, it can be any number. But just like you learned last week, when you have multiple bit inputs or multiple bit outputs, you have to put that square bracket with the number of the most significant bit and the number of least significant bit. Okay, so you'd have to have your inputs and outputs declared just like you've been doing. So there's nothing new there. Okay, that's why I didn't put anything here, because you've done that before. Okay, what's new is this: when you use an if statement in System Verilog, it always has to be within called an always comb block. See this right here? Always underscore and then COMB, comb, like you comb your hair. Comb is short for combinational. You see, all the logic circuits that we've been looking at thus far this quarter are combinational circuits. And what's meant by combinational is combinational circuits have no memory. And because they have no memory, they have no clock. Now, we're going to talk about what memory is, and we're going to talk about what a clock is in a couple of weeks. Okay, so just know they don't have it. You don't need to know exactly what these things are yet. I mean, you will eventually. But that's what makes something combinational. No memory, and if you don't have any memory, you don't need what's called a clock. Okay. So in system Verilog, to do an if statement, for a combinational circuit like we have here, you need this always underscore cone. Then you need a begin and an end for that always cone block. Okay, so you see this end down here goes with this begin. And then within the always cone block, that's where my if statement is. Okay, you can see there's an if, there's an else if, and there's an else. Okay. Else if you could have none or as many as you need. Okay, so here we only need one else if, but you might have a case where you have more options and you need more than one else if. You also might have a case where you don't need an else if, you just need an if else. Okay, so the else ifs are kind of optional, right? Sometimes you don't need it, sometimes you need more than one, right? Sometimes you just need one. You always need an else. Okay, always need to end an if with an else, unless you want a latch. Okay, sorry this is low. People in the back, if you want to move over or just come up and take a picture later on. But what I wrote here is that you always need an if with an else unless you want a latch. Okay, now you've heard that word before, right? Because where have you heard the word latch? Like, where don't you want to see the word latch? Right, when you're in Bavado and you're doing your simulation, right? And if you get a warning that has the word latch in it, we've been telling you, you got to get rid of that. See, what you're going to learn in a few weeks is that when we want memory, we want a latch. A latch is a piece of circuitry that is part of memory. So because we're only doing combinational circuits at this point, right? We're doing circuitry that doesn't have memory. Well, we don't want latches, okay? Because if you have unintended latches, that's additional circuitry that can cause problems. Now, in this class, because the designs, compared to that microprocessor that you do next quarter, CPE133, because the designs in this class are relatively simple compared to something like that, you could possibly create an unintended latch in one of our designs, and it would still work the way it's supposed to work. Even with that additional circuitry, it could still give you the truth table you want. But the reason we have you avoid latches is to get you in the habit the next class, because when you build that microprocessor, if you have unintended latches, it's not going to work, guaranteed. Okay, because the timing is much more critical in a microprocessor than in these designs that we do in here. Okay. But anyway, getting back to this, else if you could have 0 or you could have as many as you want, but you always have to end an if with an else unless you want a latch. Okay, now the other thing is, notice that the if statement or the if line here has a begin end. The else if has a begin end. And the else has a begin end. And then notice within each if, else if, and else, I list all three outputs. So yeah, I'm putting all three values, right? You know, we're saying if A is greater than B, I want the greater than to be 1, all other outputs 0. If we got the opposite, right, A less than B, well, I want LT as a 1, and the other two outputs a 0. And if they're equal, I want the equal output to be a 1 and the other two to be 0. Okay. Well, there's another way. Oh, by the way, let me put a disclaimer here. You know, I wrote this from memory. I didn't have it like it written out. So there could be syntax errors here. I'm pretty sure everything looks right. The only thing I'm not like 100% sure on, because I can't remember, is I'm not sure if these get separated with commas or semicolons. I know this is a semicolon, but I'm not sure whether these are semicolons or commas, but it's basically right. But if you were to take this and copy it down into Vado, don't be surprised if there's like a syntax error, because again, I did it from memory. But there's another way to do this. Okay, so this is one way to do that comparative. Okay? But there's another way where you can use what's called an initial block, where you initialize the outputs to some value, usually 0. So in this other way, you know, this would all be the same. You still got to declare your inputs and outputs like we said. But starting here, or between where you declare your inputs and outputs and where the always home begins, you would insert an initial block. So you see, you would type initial, and then that initial has a begin end. And then you would just set your outputs all to 0. This is, you know, initializing outputs to 0. Okay, then comes the always home. And you see, because I initialized all the outputs to 0 to start with, now I don't have to list all three outputs within my if statement. See, now I can just say, well, if I have this, I just want greater than to be 1. If I have this, I want less than to be 1. If I have equal, you know, or else, which is equal, I want equal. So you see, if you initialize all your outputs initially, then you don't have to list like all outputs if you don't initialize, like we did here. Also, if you only have a single output, you don't need the begin end like we did here. See how we had the begin end for each? That's because we had the list outputs. Okay, we don't have it here because we initialized everything to 0, and then we're just changing what needs to be changed. Okay, and you know, either way is good. You know, some people like to do this, some people like to do this. So, you know, I think this is a little less to write, but yeah, again, they're equally good. Okay, but I just wanted to show you both ways. Okay, now again, you are not doing a comparator for lab 3. This is just an example. Now, you may use a comparator for your final project. So, you know, this is something you want to hold on to because you may use it. Okay, but for none of the labs do we use a comparator. Okay, what you're going to design with an if statement is a mux for lab 3. And that mux is just a 2-to-1 mux. Right? You see this mux right here? We got 2 inputs, 1 output. We got our select line. How many bits is the select line going to be since I only have 2 inputs? Yeah, it's just a single bit select. Okay. And our inputs and also the output. I forgot to put the output over here, but the output has the same number of bits, right? So you got 4 bits coming in, 4 bits going out. Okay, so can you roughly see what your if statement's going to look like? So I'm going to have if what? So it's like, what's determining what the output's going to be? The select. So you could just do something like, you know, if select, right? If you put if select, that means when select is 1, this is going to happen, right? I want the output to be this. Do you need an else if in this if statement? No, there's only two possibilities, right? So it's either this is a 1, I want this to happen, else it's a 0, I want this to happen. Right? So it's a very simple if statement to do this mux.
So, like in traditional coding languages, equals equals is used for comparisons. Is it the same for auto?
Yes. Yeah, like you need double equal, is that what you're saying? That's true. Also, yeah, because have you had C language? Is that because it's like that in C? See, Verilog is based off the C language. So I mean, if you know C language, you're going to see a lot of similarity between Verilog and C. Yeah, the other thing is, when you were writing Boolean expressions, we were using the tilde for not. Well, that's for what's called bitwise when you're doing like a Boolean expression. When you're doing like an if statement, if you want like not something, it's exclamation point. So if you, instead of going if select, which means, select is 1, if you did like if exclamation select, that would be if select is 0. Okay. Let's see, what else was I going to say? I think that's all I wanted to say about this at this point. I think the next thing was to look at the activity on Canvas and also the lab 3. But again, any questions up to that? You're going to do this. That's why I'm not writing it all out. But if you understood this, because this is more complicated than what you have to do for the mux. The mux, like I said, it's just going to be an if and an else. You don't even need an else. Okay, so does everybody get an idea what to do for the mux? Okay, let's look at Canvas real quick. It's only going to take another 5 or 10 minutes, and then you can get started in your groups.
I don't work on
Yeah. Here's a look at the activity. Coming on. Not good. Okay, well, I don't know why. Yes, we have technical difficulties. Sorry. Can you tell us what's going on? Oh.
Oh yeah, it's on the X3 dark.
Oh, there we go. Okay, that's fine. Oh, wow, okay. Your eyes are much better than mine. Okay, now it's coming. All right. Okay, so again, I know the resolution isn't the greatest on the screen, but again, it's on Canvas, so you can see it better there. But there's 3 problems, 3 timing diagrams. And you're to do the same for each. Now, the last one has a mux along with the end. Like the top 2 are just the muxes. So, you're given what the select line is equal to. Now, this is in hex, 0x and a number. So these selects are in hex. And in this particular example, you're just given what the single bits are. So, here's D0, D1, D2, D3. So you got these 4 D inputs going in, you got your select, and here's your output. So you just got to look at what the select is and then just write what the output is, what input the output's going to equal. And then the second one, it's the same idea. The only difference between this first one and the second one is that here the bits are actually given as single bits, 0, 1, 2, 3. Here, the 4 bits are put together and expressed as a hexadecimal number, right? So if D is a hexadecimal 1, what does that mean about our 4 bits? Because what is 1 in hex equal to in binary? The 0001, right? So your least significant would be a 1, right? D0 would be a 1, and then D1 would be a 0, D2 would be a 0, D3 would be a 0. So this is just like a shorthand way of writing what was done up here. This is like the long way of doing it. This is like the short way of doing it. And then, like I said, the last one is just a 2 input mux, 2 to 1 mux along with an AND. Okay, but again, the way you look at these timing diagrams is you just start on the left, work your way right. And anytime there's a change, like here, anytime there's a change in select, that's when you have to like reevaluate what the output's going to be. Okay, so any questions about the activity? Now, just like previous, well, actually, I made an exception last week, right? Where I said, when you're doing the, let's see, what was that activity? That was the structural model, right? I said that, not each person had to do all 3 because I felt it was kind of overkill. But just like before last week, last class, and also I believe for the rest of the quarter, each student has to do all the problems again, and then just, one submission per table. Also, just as a reminder, because last week in a couple of my sections, there was a few people that left before their table was done. Remember, to get credit for the activity, you do have to stay until your table is done, not when you're done, okay? Because it's a group effort, okay? So if you're gonna leave for the lab portion, what I would recommend, if you plan on leaving after the activity is done for your table, be the person that turns it in. That way you're sure that you're not leaving beforehand, okay? So I just wanna reemphasize that. Okay, lab 3. Lab 3 looks like this. And the only thing you're doing today is you're building this mux. And when you build this mux, don't worry about what this mux is connected to. See, the input to this mux is connected to this binary data. Don't worry about that today. I'll talk about how you do that in Verilog on Thursday. You're just doing this. Okay, you're just doing this. You've already done an RCA, right? That was the lab 2. So, like I said before, for each of the labs, have your own project. So for lab 3, you're going to have a new project, and you'll create the mux in that new project, and then you can just add the RCA that you did last lab into your new project. Okay, because provided you had a successful RCA, you already have one of these that works. Okay, so you're just using what you have here. You're building this today. Again, don't worry about the binary, just do this. And then on Thursday, we're going to talk about decoders, and you'll learn how you're going to model this decoder here. And then also on Thursday, you'll be able to do a structural model to connect this all up. Because just like you connected your adders together to get the RCA, you're going to connect up these low-level diagrams, boxes, to make the overall circuit. And we'll talk about what this circuit is doing also on Thursday. Okay? So do you have any questions before you get started? Everybody ready? So work on the activity. Once that's passed in, if you want to go somewhere else to work in the lab, that's fine. But you got a lot to do, so. If you have questions, let me know. Also, Kathy will be here in about 50 minutes. She'll be here around 10.